Okay, section 1.4, complex numbers. Up until now, we've been working with real numbers. So here's our chart for real numbers. And you don't have to memorize this chart or anything, but there are different types of numbers. So the numbers you learn about when you're in elementary school, natural numbers, 1, 2, 3, 4, so on. Then you got whole numbers, which include 0. Then you get somewhere into middle school and you learn about negative numbers. And then you go a step out before that and notice up to this point, nothing had been decimals or fractions. So then when you go out to fractions and terminating or repeating decimals, you get rational numbers. You can think of rational numbers really as fractions. And then on the other side, kind of disjoint from rational numbers, are irrational numbers, which are non-repeating, non-terminating decimals, things like pi, square root of 2, that those are irrational. And so that's everything we've been talking, what we've basically been using so far, and then we call all those guys real numbers. And for many things that we're going to be doing, that's enough numbers, so to speak. But there are some applications where that's not enough numbers, or different types of numbers. So now we're going to introduce the imaginary unit I. The imaginary unit I is defined as I equals the square root of -1, or that I squared is -1. It's important to remember that I squared is -1. If you think about all the mathematics you've done, you've never used I as a variable because I squared is -1 and I represents the square root of -1. Now, one of the most important things we're going to do with this imaginary unit I is just to simplify square roots. So if we look at this showing every single step, this would be 25 times -1, which would be the square root of 25 times the square root of -1, which would be -5i. Showing way more detail than I would ever expect to see. My hope would be that you would just look at square root of -25, negative the square root of -25, and just write down -5i. The thing I really wanted to emphasize here is those two negatives don't cancel each other out. Anytime you have a negative inside a square root, you are going to have an I. So let's work on this guy. And the first thing I'm just going to acknowledge is that those negatives are going to give me i's. So I'm just going to take care of that right away and say that the negatives, bring those out as the symbol I, as the imaginary unit. Then simplifying some more. Remember when you simplify radicals or square roots, you're looking for two numbers who multiply to be the number in question, in this case 32, two numbers that multiply to be 32, one of which you know the square root of. And a good choice here is 16 times 2. Then for the 18, the same thing, two numbers that multiply to be 18, but one of which that I know the square root of, 9 times 2. Now yes, 3 times 6 multiplies by 18, but I don't know the square root of 3, I don't know the square root of 6. And same thing with 32, you could do 4 times 8, but 16 times 2 is a better choice. Then continue to simplify. And again, I'm showing every step I can think to show. Square root of 16 is 4. Can't do anything with the 2, so that's left behind. Square root of 9 is 3. And so that's going to give me 12i square root of 2 minus 12i square root of 2 for answer of 0. Okay, doing the same thing here. So what this is going to start out as 3i square root of 75 minus 2i square root of 12 plus 3i square root of 50 plus the square root of 21, which is then going to be 3i. 75 I can rewrite as 25 times 3. 12 I can rewrite as 4 times 3. 50 I can rewrite as, 25 times 2? And then I come up with the 21, and there's nothing good for the 21. Yeah, 21 is 3 times 7, but I don't know the square root of 3. I don't know the square root of 7. Keep going. I'll have to write smaller here if I get it all on there. Square root of 25 is 5, leaving behind the square root of 3. An equal sign. Minus 2i times 2 square root of 3 plus 3i times 5 square root of 2 plus the square root of 21. We will drop down here. I didn't plan my space well. So we got 15i square root of 3 minus 4i square root of 3 plus 15i square root of 3. And then on the end, square root of 21. Then these are all like terms here. 15i square root of 3 minus 4i square root of 3 plus 15i square root of 3. And so that's going to be negative 4i square root of 3 plus the square root of 21. And that problem is done. So right here, 15i square root of 3. Oh, that problem is not done because I did it wrong. So pretend that last line didn't happen. I misread my own handwriting, so let's white that out. Love the whiteout. Just combining my coefficients here. So 15i, 4i, or minus 4i, 15i. These are all like terms, so I can combine them. 15i minus 4i would be 11i. 11i plus 15i would be 26i square root of 3 plus the square root of 21. And that guy is done. We no longer have any like terms, so that one is done. Okay, the next guy. And this sort of thing is actually going to creep up in your work quite a lot. Simplifying this. First and foremost, the 14 and the 2 do not cancel. You do not cancel in a fraction unless you cancel from all terms in a fraction. So I am not going to cancel that negative 14 and the 2 because I can't do anything with that square root of negative 45 and the 2. So let's just work with that square root of 45. The I can come out. That's what the negative inside there does. And now working with the 45, 45 is 9 times 5. Again, you pick two numbers that multiply to be the number in question, in this case 45, one of which you know the square root of. I know the square root of 9. Then the square root of 9 can come out as a 3, and that problem is done. Nothing cancels. You cannot cancel in a fraction unless you cancel from all terms in a fraction. And so because I can't cancel the 2 from the 3i squared of 5, nothing can happen. Okay, next guy's pretty similar. So we'll start similarly. That I comes from the negative, so pull that on out. Then work with the 75. 75 is 25 times 3. And then the square root of 25 is 5. And now we can note that all terms are divisible by 5. All terms are divisible by 5, so I can do that. I can divide everybody by 5. Divide by 5. Everybody. And so very explicitly, I'm going to get 6 plus 1i square root of 3 over 1, being very, very, very explicit. But you do not have to write coefficients of 1. You do not have to write denominators of 1. So this is 6 plus I square root of 3. And so the real point between these last two examples is when can I cancel? When can't I cancel? Here on this one, nothing ever canceled because I never had everybody divisible by 2. This wasn't divisible by 2. But here, all the terms were divisible by 5, so I could divide by 5. Okay, moving on a little bit. So then our chart of numbers gets reorganized like this, where we now just tack on the imaginary numbers to the real number side. And again, you don't have to remember the organization of the numbers, but these guys are now imaginary numbers. And when we put everything together, all those guys put together are called complex numbers, or we'll get the complex numbers there. But they're my imaginary numbers. And so then definition down here, the set of all numbers, a plus bi, with real numbers a and b and I, the imaginary unit, is called the set of complex numbers. The real number a is called the real part. The real number b is called the imaginary part of the complex number a plus bi. If b does not equal 0, the complex number is called an imaginary number. Imaginary number in the form bi is called a pure imaginary number. Now, you don't have to remember really any of that whatsoever, other than a plus bi is now this thing called a complex number. So when we add that phrase into it, there's our chart of numbers that everybody is a complex number. Real numbers are complex numbers, imaginary numbers are complex numbers, everybody is a complex number. And again, you do not have to remember the organization of this chart. But complex numbers, even with the i's, they are numbers. And just like you can add, subtract, multiply, divide, quote unquote, regular numbers, or what we've been working up to on this point, real numbers, you can add, subtract, multiply, divide complex numbers. For adding and subtracting and multiplying, you would proceed as you would any other expression, distributing and foiling where necessary, combining like terms. That it's going to feel very normal how we're going to add, subtract, multiply complex numbers. But every time we get an I squared, you're going to remember that it's -1. And so whenever you have an I squared, you're going to replace it with -1. So we are just going to practice adding, subtracting, multiplying complex numbers. And so pretty much you can treat this exactly the same way as you would combining like terms if there was an x there. It's just that the I isn't a variable. It represents a specific thing, square root of -1, but you can treat it just like you would as if it was an x. Now, frequently you will see things, complex numbers grouped together in parentheses, but since there's a plus sign between these two parentheses, it's not doing anything. And so this is the same as 6 minus 5i plus 4 minus 9i, and then just combine my like terms. 6 plus 4 is 10. -5i minus 4i, -14i. And that guy is done. Now, express in standard form. That means a plus bi or a minus bi is what standard form means. And now, while I won't be particularly picky, I just want a right answer on these guys. If the computer says standard form, you give it standard form. That if you permute those two and say -14i plus 10, the computer will count it wrong. So standard form, you put the real number first, the imaginary number second. And we'll end this video and start with the next one.